All right. So what we are going to talk about today is a continuation of Lewis structures. Any questions on Lewis structures from yesterday? No? Okay. But what if I said that there are even better, more correct ways to draw Lewis structures for certain compounds? Would you say yay? I would hope so, because there are better and more correct ways for us to draw Lewis structures. Because yesterday we did, I think, well, actually, did we get to PO4 3 minus? I don't think we did we? Okay, well, let's start with that one first. And then, because this particular one is one that I want us to remember kind of as we continue on with our discussion today. So if we look at, I'm going to do this one on the whiteboard just so it's documented. Okay. We have PO4 3 minus. And I think I made a boo-boo. I certainly did. So I'm just going to actually turn the camera, and hopefully they can see that. Okay. So we'll get back into this. And yeah, we'll do it over here so there's no glare. All right. So right back up here. PO4 3 minus. What's the first step in writing Lewis structures? We have to sum the valence electrons for all atoms involved, right? How many does phosphorus have? What did you say? 5. Very good. And a single oxygen has how many? 6. How many are present? 4. 6 times 4 is 24. Okay, so initially we have 29. But we're dealing with an ion here. Okay? We're dealing with an ion here, and it has a charge of -3. So what does that mean we have to do for in terms of the total number of electrons? Do we add or subtract electrons? Add. And how many are we going to add? 3. So we have a total of 32 electrons that we have to deal with. Now, one thing I think I forgot to mention yesterday when we were doing ClO2 minus. Okay? Again, these are polyatomic ions, also known as oxyanions. Why do we call them oxyanions? Any guesses? Because they contain oxygen, yes. And there's a rule of thumb with oxyanions as to who goes in the middle. When we have oxyanions, the oxygens go on the outside automatically. Okay? So it makes our job pretty easy when it comes to determining who our central atom is. It's going to be phosphorus. So go ahead and jot down P. And then following our steps that we talked about yesterday, we are going to just go ahead and connect the outer elements with single bonds. Now, in the process of connecting those 4 oxygens, how many electrons were used? If each line represents 2, 8. So, keeping track, I have 24 to deal with. Okay? Now, according to the steps from yesterday, I then have to fill the octets of the outer atoms. And so far, each outer atom, we say, has 2. So how many do they need to fill the octet? 6. Okay? So then I use dots. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. If the math is correct, by placing 6 electrons on each of the oxygens results in the use of 24. And so I have used up all my electrons. So after you've used all the electrons, take a step back and ask yourself, is every atom happy? Do they have an octet? What do you think? Yes. Yes, they are. Good. In your morning robot voice. All right, yes. Now, since everybody's happy, can I put my stamp of approval on and move on to the next one? Right. Yes. Remember, it's an ion. So we have to use brackets around the whole thing. Not only do we have to include brackets, but what also do we have to include? We have to include the charge in the upper right-hand corner outside of the brackets. So that would be our completed Lewis structure for PO43-. But that's where we get into today's discussion. Okay? We are going to, excuse me, look at a method for us to determine what is the best Lewis structure. And we do that through a process called formal charges. Okay? So, formal charges, just a little background, are not real charges. They really are a means for us to assign electrons appropriately so that in the long run it kind of makes sense. Okay? So, for each atom, what you're going to do is you're going to count the electrons in lone pairs. So if you have 3 electrons that are not bonded, so if you have 3 dots, you're going to do 1, 2, 3. And for any shared electrons, you're going to half them. So, for example, if I have, again, this is just an imaginary one. If I had P and oxide, phosphorus and oxygen bonded with a single line, again, a single line represents how many electrons? 2. So, when assigning formal charges, I half them. So, if I split that in half, how many goes to phosphorus? 1. How many goes to oxygen? 1. That's what that means. Okay? And so, when you're doing this, you're going to subtract the number of valence electrons for each atom. And this is what gives us our formal charge. So, anytime you do this, what you want to do is set up this kind of little table here, okay, where you have the valence electrons, which the valence electrons, the value you give here is how many they have if you just look off the periodic table, okay? For instance, we have this compound right here, CO2. pretty common compound. And this would be one form of its Lewis structure. Okay? So, you have your valence electrons. Oxygen is, if you look off the periodic table, 6. Okay? Carbon, if you look off the periodic table, is 4. Again, another oxygen would be 6. Then you subtract from those values the electrons that are assigned to that or to those atoms. And what that means is, how many electrons did you give it in the Lewis structure? So as you notice that they kind of have it set up to where they have lines that are bisecting those bonds. See that? Everybody see that? So let's practice counting. All right. First, 1, 2, 3, 4 non-bonded. Can anybody tell me how many electrons would be placed on oxygen after we bisect those double bonds? There you go. How many? One each, but 2. Very good. So total assigned to oxygen would be 1, 2, 3, 4, 5, 6. So then you put 6 right down here. And you do the same thing for the other remaining ones. Again, these double bonds are bisected on carbon. So you get 1, 2, 3, 4 assigned to it. Place that 4 there. Same thing with the last oxygen here. 1, 2, 3, 4, 5, 6. Place it there. Do your math, and you get all zeros, which is really what you want when it comes to a neutral compound. Now, you want all zeros. Now, just to show you another example about how a Lewis structure could technically be designed is this on the right here, okay? You could have a single bond between one of the oxygens and carbon, and then a triple bond between the other oxygen and carbon, okay? But, again, that doesn't look right, but we won't know until we do the formal charge. So we follow the same process. We have the valence electrons for each, as we would see from the periodic table. And then we go and start assigning electrons to each atom. So if we look at this right here, this oxygen on the left, 1, 2, 3, 4, 5, 6, 7. We have 7 electrons assigned to that oxygen. So you put 7 here. Move on to the carbon. You still have 4 assigned there. And then this oxygen on the right, you've got 1, 2, 3, 4, 5 electrons assigned to it. You put a 5 there. So now, doing your math, you have a -1 on the left oxygen, a 0 on the carbon, and a +1 on the right oxygen. Now, if you were to sum this up, what would your final result be? 0. So you still get 0. So how do you determine which one of these is best? We have a few more rules that we have to follow. The best Lewis structure includes these. The one that has the fewest charges, and if you have to, it puts a negative charge on the most electronegative atom in the molecule. So if we look at these 3 examples here, okay? And we compare them. Let's actually do the formal charges on here, okay? So, yeah, I'll do it one at a time here. So we have the first compound on the left. We've got N. We've got carbon, and we've got oxygen. And it's a polyatomic ion. Okay. Now, we wouldn't necessarily. Well, never mind. I don't want to say anything since that has nothing to do with this. Let's calculate. Even though it shows us the formal charges above it, I want to walk you through it. Okay. So again, we've got the valence electrons here minus the assigned electrons. This is going to give us our orbital charge. Okay, so first thing is we're going to set up our columns. And we do that by bisecting our bonds. Okay? It's also a visual for you to show that we are splitting those electrons in half. So nitrogen. How many electrons does nitrogen have if you just pull it off the periodic table? 5. Okay. Carbon. 4. Oxygen. 6. Okay. Now, let's look at the Lewis structure itself to determine how many are assigned. If we look at this nitrogen, we've got 1, 2, 3, 4, 5, 6, 7. We have 7 electrons assigned to that nitrogen. How many do we have for carbon? 4. 1, 2, 3, 4. And how many do we have for oxygen? 5. 1, 2, 3, 4, 5. So we go ahead and do our mathing. Minus 2 on there, 0, plus 1 there. And again, if you were to sum up these formal charges, you would end up with minus 1, which should match the charge on the ion. Okay? Now, does everybody understand this process? Okay. So now that we kind of understand the process and we know what these values now kind of mean, we need to pick up which of these 3 Lewis structures would actually be the best Lewis structure. Okay? So let's look at the first bullet point. It would be the one with the fewest charges. Is there any one of these 3 that we can go ahead and discount, get rid of right off the bat? First one, right? It's got a whole bunch of charges going on here. Which leaves us with these 2 remaining. Okay? So again, their overall formal charges equals that of the ion, so that's good. But they have equal charges. Okay? So then we go to bullet point number 2. It puts a negative charge on the most electronegative atom. So on this middle one here, it places the minus 1 on the nitrogen. And on the second one over here, it places the minus 1 on the oxygen. So which one is more electronegative? Oxygen. Okay, so which Lewis structure is the best one of these 2? The one in the middle or the one on the right? The one on the right. Again, because we've minimized charges, the formal charge equals the charge on the ion, so that's good. But on the one on the right, it places the charge on the more electronegative atom, the oxygen. Now, what that means is you might be having to move some bonds around. You might have to make double bonds. Okay, you might have to remove a double bond and make a single bond. You might even have to make a triple bond. Okay, so what these do is it allows you to manipulate your Lewis structure so that you can show its best design. All right. Again, this example is just the same one as a few slides ago. Okay. Now, that brings us to the end of the section. Okay. That's why I didn't want to rush through that yesterday. So what I want you to do for the rest of the class, as well as excuse me, the over the weekend, and then we're going to, or I'll send out the solutions to classroom so you can check. All right, and then we'll talk about it on Tuesday when you come in here. If you're just thrown off by something, all right. So there is a front and a back. So you want to practice your formal charges. Actually,